Every year, millions of tons of coconuts are harvested across India, leaving behind an enormous amount of waste for decades. But today, this waste is being transformed into construction materials for thousands of kilometers of roads, creating one of the world's most successful recycling models. So how have India's brilliant engineers managed to turn coconut byproducts into the foundation of sustainable roads? And why is almost every part of the coconut being utilized to create a multi-billion-dollar industry? Join Terran Works as we explore the story behind this extraordinary achievement. Surrounded by more than 7,500 kilometers of coastline and blessed with a tropical climate, India has become one of the world's largest coconut-producing powers. Every year, the country harvests more than 21.4 billion coconuts, supporting the livelihoods of more than 12 million people and creating a multi-billion-dollar industry. But behind this enormous scale lies a paradox. A coconut consists of a commercially valuable kernel and a fibrous husk that accounts for a large share of its total weight. After processing, nearly 70% of the coconut still remains underutilized, creating an enormous source of waste every year. Meanwhile, more than 60% of India's population still lives in rural areas, where thousands of kilometers of roads are constantly damaged by monsoon rains, floods, and weak soil conditions. After just a few rainy seasons, many roads sink, erode, or are washed away, making agricultural transportation and connections between communities extremely difficult. The intersection of these two challenges created an entirely new breakthrough. Instead of treating coconut fiber as waste, Indian engineers used approximately 10 million square meters of coir geotextiles to build 1,674 kilometers of roads across 7 states, creating one of the largest large-scale applications in the global coir industry. To understand why a layer of fiber surrounding a coconut can become the foundation of sustainable roads, we must begin with the process of handling millions of tons of coconut husks every year. After being transported to the factory, the massive piles of coconut husks enter the most important stage, extracting the coconut fiber. Instead of soaking the husks in water for several months, as in the traditional method, most modern factories in India use decorticator systems to mechanize the entire process. The coconut husks are continuously loaded onto conveyor belts and fed into crushing machines. Inside, rotating shafts equipped with dozens of steel blades and high-speed hammers continuously compress, crush, and tear apart the tough husks. The impact force breaks the connective tissues between the fibers and the coconut pith, releasing long bundles of fiber without breaking their natural structure. The crushed mixture then passes through a system of vibrating screens and air blowers for separation. The long fibers are retained, while the coconut pith, dust, and small debris are removed separately. From 1 ton of coconut husks, a factory typically produces around 250 to 300 kilograms of coconut fiber. The remaining material is mainly coconut pith, which can retain water up to approximately 8 times its own weight. Today, coconut pith is widely used on vegetable and flower farms and in high-tech greenhouses in countries such as the Netherlands, the United States, Spain, South Korea, and Japan. The extracted bundles of fiber still contain dust and a large amount of moisture. They are therefore washed and spread evenly across drying yards, covering thousands of square meters under natural sunlight. Only when the moisture content reaches between 15 and 20% is the coconut fiber transferred to the heart of the entire coir geotextile production process, carding and spinning. Once the coconut fiber reaches the standard moisture level, The coconut fiber is fed into carding machines to remove short fibers and remaining dust, while aligning all the fibers in the same direction. This process makes the fiber bundles more uniform, softer, and ready for the spinning stage. Next, the fiber bundles pass through spinning machines, where multiple small fibers are stretched and tightly twisted together to form coir yarns with a uniform thickness. The twisting speed and tension are continuously controlled to ensure that the yarns have sufficient tensile strength to withstand heavy loads and outdoor conditions for many years. From these coir yarn spools, the final stage begins on wide industrial weaving looms. Here, the yarns are woven perpendicularly in both longitudinal and transverse directions, creating mesh sheets with predetermined opening sizes and yarn densities tailored to each application. Depending on project requirements, core geotextile rolls commonly have a width of 2 meters and a length of 25 to 50 meters. At this stage, these remarkable mesh sheets are ready to become a natural reinforcement layer for roads and many other infrastructure projects. With the subgrade graded to the correct design elevation, vibratory rollers and pneumatic tire rollers make multiple passes to create a flat, stable surface and achieve the required level of compaction before the reinforcement layer is installed. Once the roadbed has been approved, the geotextile rolls are transported by truck to the construction site, lifted using cranes or excavators, and positioned along the entire route. Thanks to their relatively light weight, each roll can be pulled manually by several workers before being aligned in the correct position. The mesh is then stretched to remove wrinkles and secured to the ground using steel or bamboo stakes, typically driven approximately 1 to 2 meters apart to prevent the mesh from shifting during construction. At the joints, 2 mesh sheets overlap by 20 to 30 centimeters, creating a continuous reinforcement layer across the entire road surface. Remarkably, building just 1 kilometer of rural road requires the installation of nearly 6,000 square meters of coconut fiber geotextile. Once the mesh system is completely secured, dump trucks begin placing the first layer of base material, consisting of sand, granular soil, or crushed stone, across the surface. Instead of dumping the material in large piles, it is spread evenly in thin layers approximately 15 to 30 centimeters thick to prevent the coconut fiber mesh underneath from shifting or being damaged. Next, bulldozers and motor graders distribute the material evenly across the entire road surface before multi-ton vibratory rollers compact it through multiple passes. Under the enormous load, soil and stone particles gradually fill the openings of the mesh, creating a tightly interlocked structure between the base layer and the natural ground. After the first base layer has been compacted and reaches the required design density, construction crews continue by placing an upper base layer made from higher quality graded crushed stone. Finally, the road surface is completed with asphalt concrete or cement concrete, depending on the requirements of each project. Throughout the entire lifespan of the structure, the coconut fiber mesh continues to work silently beneath the road structure, reinforcing the ground, reducing uneven settlement, and limiting erosion caused by rainwater. However, unlike synthetic geotextiles that can maintain their strength for several decades, the main limitation of coconut fiber geotextiles is that they serve only as reinforcement during the early years. After approximately 3 to 5 years, once vegetation along both sides of the road has developed and stabilized, and the ground has reached a sustainable condition, the coconut fiber layer gradually biodegrades, returning organic matter to the soil without leaving behind plastic waste. This achievement not only helps solve an infrastructure challenge, but also opens the door to a multi-billion-dollar industry where agricultural waste is transformed into sustainable economic value. But that is only half the story. To understand how this country utilizes almost every part of the coconut, we must return to the very beginning, harvesting billions of coconuts across India. A mature coconut tree typically grows between 15 and 30 meters tall, equivalent to a 5 to 10-story building, with a nearly vertical, smooth trunk and no branches to hold on to. For this reason, in many traditional coconut growing regions, farmers still have to climb directly up the trunk using only the grip of their feet, a rope wrapped around their ankles, or simple climbing devices. Just one slip at a height of several dozen meters can cause serious injury or even claim a life. For shorter trees, farmers use sickles attached to bamboo poles or alloy handles, approximately 6 to 9 meters long, to cut down individual bunches of coconuts directly from the ground. This method is safer and faster, but it is only effective for trees that have not grown too tall. Once the height exceeds their reach, climbing to the top of the tree remains almost the only option. After the coconut bunches, weighing several dozen kilograms, are brought down to the ground, the process of sorting and removing the fibrous husks officially begins. In many traditional coconut growing regions of India, this work is still carried out entirely by hand. Workers drive a sharp steel spike, approximately 30 to 50 centimeters long, firmly into the ground, then use their entire body weight to press the coconuts against the steel blade, tearing the husks into several pieces. A skilled worker can separate only around 60 to 100 coconuts per hour using this method. After being separated from their outer fibrous husks, tons of coconut kernels are collected into large batches and transported to processing factories. The coconuts, after their fibrous husks have been removed, are first sent through shell-splitting machines, where the hard outer shells are cut into 2 halves using blades or hydraulic knife systems. As soon as the shells are opened, the coconut water inside flows into stainless steel tanks through a closed collection system designed to minimize contamination and preserve its natural flavor. The coconut meat attached to the inside of the shells is then removed using scraping machines or semi-automatic equipment. The white pieces of coconut meat are further washed to remove dust, shell fragments, and impurities before being sorted according to their intended use. For coconut oil production, the coconut meat is cut into small pieces and sent through a drying system to reduce its moisture content from approximately 50% to below 3%, producing copra, the standard raw material for the oil extraction process. Meanwhile, factories producing desiccated coconut send the coconut meat directly through a processing line for grinding, steam blanching, hot drying, and cooling before packaging. The coconut water, meanwhile, is filtered through multiple stages to remove sediment, then pasteurized at high temperatures for a short period to eliminate microorganisms while preserving its flavor. This approach of utilizing almost every part of the coconut has helped India build a multi-billion-dollar industry, support the livelihoods of more than 12 million people, and become one of the world's leading centers for coconut product manufacturing. Thousands of kilometers of roads have been built from something that was once discarded. This is not only an achievement of India's coconut industry, but also proof that sometimes the solution to our biggest problems lies in the very things humans once considered waste. In your country, what agricultural byproduct is currently being wasted that could become a green material in the future? For centuries, sargassum was simply a natural part of the Atlantic ecosystem, a floating brown seaweed that acted as a biological oasis in the middle of the ocean. For juvenile fish, sea turtles, and hundreds of other marine species, it was called home. Most of it was concentrated around the Sargasso Sea, a region spanning more than 5 million kilometers in the North Atlantic, nearly half the size of Europe and 3 times larger than the Great Pacific Garbage Patch. But over the past decade, that balance has begun to collapse. Ocean temperatures have risen due to climate change, while millions of tons of fertilizer and agricultural waste have continuously flowed from the Amazon, Congo, and Mississippi rivers into the Atlantic. At the same time, shifting ocean currents have unintentionally created the perfect environment for sargassum to explode on an unprecedented scale. To this day, sargassum mass has continued reaching record levels of 37 million tons, forming the Great Atlantic Sargassum Belt, an ocean biomass belt. From NASA spacecraft imagery, many scientists have called it the brown monster of the Atlantic. The worst part is that when decomposing, sargassum releases hydrogen sulfide, a toxic gas with the smell of rotten eggs that can irritate the lungs and affect the nervous system. Many tourist beaches across Mexico and the Caribbean have been forced to shut down for weeks, causing billions of dollars in losses every year. But the very thing that makes sargassum a disaster is also what makes it extraordinarily valuable. Because behind the biomass covering the Atlantic lie tens of millions of tons of organic carbon, cellulose, alginate, and marine minerals. And perhaps the most absurd part is this: the biological nightmare spreading across the Atlantic is now gradually becoming a new raw material reserve for post-carbon civilization. Unlike oil or minerals that can be stored for years, sargassum only truly retains its value while still fresh. After just a few hours under tropical temperatures, this entire biomass rapidly begins decomposing, releasing hydrogen sulfide, losing its cellulose structure, and turning into foul-smelling biological waste. That has pushed the coastal regions of the southern United States, the Caribbean, and Mexico into an entirely new race, collecting millions of tons of seaweed before it has time to rot. At first, most sargassum was handled directly on beaches using bulldozers, tractors, and mechanized conveyor systems, operating almost around the clock. During the 2018 outbreak alone, the Caribbean spent around $120 million cleaning seaweed from coastlines. Meanwhile, South Florida once estimated cleanup costs could reach up to $40 million annually just to protect tourist beaches. If you were paid around $5 an hour, would you be willing to stand for hours in temperatures above 35 degrees Celsius, shoveling tons of seaweed reeking of hydrogen sulfide and sewage-like odors? But beach collection methods quickly revealed their limits. Bulldozers often removed large amounts of beach sand along with the seaweed, causing coastal erosion and damaging shoreline ecosystems. At the same time, sargassum landings across the Caribbean were once estimated at nearly 10,000 wet tons per day during peak periods, equivalent to hundreds of biomass trucks. And that was when the battle began shifting out into the open ocean. Humanity actively started hunting ocean waste. This process usually begins with floating barriers stretching hundreds of meters, deployed parallel to coastlines, to block and gather sargassum into massive offshore clusters. Specialized harvesting vessels then move along these biomass corridors, using conveyor belt systems and floating suction pumps to continuously pull seaweed from the ocean surface into onboard storage compartments. Some harvesting vessels operating in Mexico and the Caribbean can now collect between 40 to 100 tons of sargassum per day. Compared to direct beach collection, offshore harvesting allows the biomass to remain fresh, preserving much higher levels of cellulose, alginate, and organic carbon, critical factors for the biomaterials and biofuel industries. But collecting millions of tons of sargassum is only the easiest part of this crisis, because the real challenge lies in figuring out how to unlock the enormous potential of this chaotic biomass and transform it into stable industrial feedstock for large-scale manufacturing. One of the companies leading this race is Sargablox, a Mexican startup attempting to transform millions of tons of sargassum into construction materials for the promising low-carbon economy. Omar de Jesus Vázquez Sanchez started almost from nothing, beginning with small crews collecting seaweed along the coastlines of Mexico. The brick manufacturing process usually begins immediately after the sargassum is transported from coastal collection sites to processing factories. After undergoing initial impurity removal, the seaweed is then further dried down to roughly 15 to 20% moisture content before being shredded into biomass fibers and mixed with clay, lime, biopolymers, or cement, using proprietary formulas to create a biocomposite mixture. This mixture is then fed into high-pressure molds capable of producing nearly 500 bricks per hour, creating construction blocks approximately 3 times lighter than traditional concrete, significantly reducing transportation costs and structural load weight. Thanks to the biological fiber structure that traps air inside the material, homes built with sargassum bricks can reduce indoor temperatures by around 5 to 7 degrees Celsius during summer, while also maintaining more stable heat retention during winter. So far, more than 13 homes for low-income families in Mexico have been built using this material, with each house utilizing nearly 20 tons of recycled sargassum. And that is exactly why the construction industry has begun paying attention to sargassum. The cement industry alone currently emits more than 2.5 billion tons of carbon dioxide every year, while sargassum represents a free biomass source on the scale of tens of millions of tons continuously washing ashore across the Caribbean and North America. But turning sargassum into stable construction material remains a highly complex engineering challenge, as this biomass still carries potential contamination risks and long-term health concerns. And although the future of sargassum in the construction industry remains highly controversial, many companies now see this ocean biomass as a potential solution to the hundreds of millions of tons of petroleum-based plastic gradually engulfing our planet. Every year, the world produces more than 400 million tons of plastic, most of it made from petroleum, and around 11 million tons of that eventually flow into rivers, lakes, and oceans as plastic waste. That is why the ambition of the bioplastics industry is far greater, transforming sargassum into a direct replacement for single-use plastic packaging. Thanks to its natural biofilm forming ability, sargassum, after being desalinated, shredded, and polymer extracted, can be processed into biodegradable films, packaging materials, and food containers capable of naturally decomposing after use. But that is also what creates the greatest challenge. Unlike algae biomass cultivated in stable and expensive controlled environments, sargassum constantly changes its biological composition with the seasons, making polymer refinement far more complex. Yet the ambitions surrounding sargassum still do not stop at biomaterials, because the true gold mine of this ocean biomass lies in its potential to become a nearly limitless energy source for the future. This process usually begins by shredding and drying sargassum before feeding it into anaerobic digestion systems, oxygen-free decomposition systems that use microorganisms to break down the organic compounds inside the biomass. In an oxygen-free environment, millions of microorganisms continuously decompose the seaweed to produce methane and biogas, which can then be used for electricity generation, heating, or further refined into industrial fuel. Remarkably, if around 1 million tons of dry sargassum were processed, the methane produced could theoretically generate enough electricity to power approximately 30,000 to 40,000 households for an entire year. In the Caribbean, Dr. Legina Henry is pursuing an idea once considered absurd, transforming the foul-smelling seaweed covering coastlines into fuel for transportation and future energy systems. Her innovation led to experiments mixing sargassum with wastewater from the rum production industry and blackbelly sheep manure before feeding the mixture into anaerobic digestion systems to generate biomethane. The resulting gas is then further purified to remove carbon dioxide, hydrogen sulfide, and impurities before being compressed at high pressure into bio-CNG, a fuel that can be used directly in natural gas vehicles and industrial power generators. Some early experiments suggest that bio-CNG could reduce fuel costs by nearly half compared to traditional gasoline, while the amount of energy generated from roughly 1 ton of dry biomass would be enough for a natural gas vehicle to travel more than 120 to 150 kilometers. In a more distant future, if something once considered ocean waste can become fuel for transportation, it may also become part of the low-carbon energy systems powering the industries of the future. Beyond fuels and biomaterials, sargassum is now also being explored for the production of textiles, fertilizers, and even livestock feed additives. More remarkably, several companies have recently begun experimenting with turning this ocean biomass into biodegradable paper with lightweight and durable properties, while decomposing faster than many forms of traditional wood pulp paper. And as sargassum begins to be viewed as a strategic biomass resource, the game surrounding the Atlantic is rapidly changing. From Mexico and the Caribbean to the U.S. Gulf Coast, startups and coastal governments are racing to build harvesting fleets, biomass terminals, and industrial supply chains in order to secure control over the enormous marine feedstock continuously appearing across the ocean every year. Because in the future, low-carbon economy, controlling ocean biomass could also mean controlling fuel, biomaterials, and part of the new energy infrastructure of the 21st century. From a biological disaster in the Atlantic, sargassum is now gradually becoming a test of how humanity can transform the climate crisis into the post-carbon economy of the future. So in your opinion, is sargassum truly a new gold mine of the green economy, or simply an overly ambitious experiment by humanity? And while that race unfolds, somewhere else in the world, the disappointment of a teenager after his very first scuba dive was igniting the largest ocean cleaning campaign in human history. At the mouth of the Jones Falls, as it empties into Baltimore's Inner Harbor, stands an unlikely celebrity in American environmental engineering, a solar and water-powered trash interceptor, complete with playful googly eyes, known as Mr. Trash Wheel. But behind its lighthearted appearance lies an ingenious idea rooted in an ordinary, everyday observation. The idea came from John Kellett, an environmental scientist and former director of the Baltimore Maritime Museum. Each day, as he walked across a footbridge, he watched trash flow into the harbor like a never-ending conveyor belt, year after year, in one of America's most trash-impacted urban watersheds, funneling vast amounts of debris toward the Chesapeake Bay. In 2006, Kellett called the city with a simple question. Were they willing to listen to a different idea? The response he received promised nothing extraordinary, but it was enough to begin. They were willing to listen. What Kellett proposed sounded almost like a visual trick. By harnessing the river's own current to turn a wheel, the machine would lift floating debris onto a conveyor belt and deposit it into dumpsters. In 2008, the Able Foundation provided $375,000 to fund a prototype. After years of refinement, the fully realized version of Mr. Trash Wheel was officially deployed on May 9, 2014. What happened next exceeded every projection. Within its very first week of operation, Mr. Trash Wheel collected 11 tons of trash in a single day, a figure that surprised even its strongest supporters. By April 20, 2015, after heavy rains pushed debris downstream from upstream areas, the machine pulled 19 tons of trash from the water in just 24 hours, equivalent to 38,000 pounds. These figures were no longer symbolic proof, but hard data. Baltimore moved quickly to scale the model. Professor Trash Wheel was launched in December 2016 after a crowdfunding campaign raised $550,000. Captain Trash Wheel followed in June 2018 under the ownership of the Maryland Port Administration. By June 2021, the largest member of the fleet, Gwinda the Goodwill, was deployed, equipped with 72 solar panels and a grappling arm powerful enough to handle larger debris. Taken together, the Trash Wheel family has removed more than 2,500 tons of debris, over 5 million pounds, before it could escape downstream into the wider river system. Among the collected waste were nearly 2 million plastic bottles and 12.6 million cigarette butts. And in 2015, the machines even retrieved a live ball python, a moment that went viral on social media. In 2023, a new record was set when the Trash Wheel family collected more than 1 million pounds in a single year. These numbers can easily inspire optimism. But this is precisely the point where a more difficult question must be asked. Is this merely a symbolic solution, or a model that can operate sustainably at an economic and systemic level? Each trash wheel costs between $400,000 and $800,000 to build, with annual operating expenses ranging from $100,000 to $200,000. Viewed in isolation, these are not small figures. However, when calculated per pound of trash removed, the cost comes to roughly 20 cents, significantly lower than that of traditional skimmer boats. Baltimore's Department of Public Works spends approximately $1.3 million per year on harbor operations and collects about 420 tons of debris. By comparison, the trash wheels remove more trash at a lower cost. This makes clear that what we are seeing is not a technological miracle, but efficiency created by placing the right technology at the right bottleneck in the flow of waste. The greater value of the trash wheels lies not in the volume of debris they collect, but in the data they generate. After Maryland implemented a statewide ban on foam containers in 2020, the trash wheels recorded an 85 to 90% reduction in foam debris. Plastic bag bans led to a 72% drop in the number of bags collected. These figures are not estimates, they are direct, on-the-ground evidence. Adam Lindquist, former director of the Healthy Harbor Initiative, once said that their ultimate goal was to put Mr. Trash Wheel out of a job. This was not a joke, but a long-term vision. When waste is eliminated at its source, collection technology becomes unnecessary. In April 2025, the Baltimore Ravens and the Bisciotti Foundation announced a $3.75 million 5-year partnership aimed at removing an additional 5 million pounds of trash and growing 5 million oysters by 2030. A 5th trash wheel is now also in the planning stages. 3,000 miles to the west, Los Angeles faced a very different challenge, one operating at a much larger scale. That effort traces back to a moment far removed from Los Angeles itself. When a teenager named Boyan Slat returned from a diving trip frustrated by the plastic he saw beneath the surface, a moment that would go on to spark one of the largest ocean cleanup initiatives in human history. When the ocean cleanup deployed Interceptor 007 to Ballona Creek in October 2022, engineers relied on historical data and estimated that the system would collect roughly 60 tons of trash during its pilot phase. Reality far exceeded those expectations. The Interceptor collected more than 125 tons, over 250,000 pounds, more than double what had been projected. The paradox is that these numbers can point to two very different conclusions. Either the technology performed far more effectively than any calculation anticipated, or the people of Los Angeles were discarding twice as much waste as engineers had ever accounted for. During the 2022-2023 storm season alone, the Interceptor captured 155,000 pounds of debris, nearly two-thirds of it plastic and other inorganic materials. A single collection event removed nearly 20,000 pounds. In October 2024, LA County voted unanimously to make the Interceptor a permanent solution, with more than $250 million allocated to projects across the Los Angeles River watershed. Alongside technology, community efforts have remained indispensable. Friends of the LA River, founded in 1986, has mobilized approximately 50,000 volunteers over 34 years and removed a cumulative 1.6 million pounds of trash. Ecological recovery is now becoming visible. The endangered least Bell's vireo, absent from Taylor Yard for decades, has returned. Los Angeles' $11 billion federal ecosystem restoration project is now regarded as one of the largest urban restoration efforts in the world, with completion targeted for the 2028 Olympic Games.